All right, so let's take a look at the next Rust project, and I'm just going to describe this one, I think. We talked about string buffer overflows, which were on the stack, and you can also have string buffer overflows on the heap. If you use a malloc in C to allocate some space, say 20 bytes, you can then put in objects, name1 and name2, and just like on the stack, C does not limit how much you put in there or move it when it gets big. So if you put in things that are 20 characters long, it works fine. Name1 gets the A's and name2 gets the B's. But if you put in things that are 40 characters long, then name1 gets some horrible mess with A's and B's in it, and name2 gets B's, and it overlaps them so it can't even figure out where one ends and where the other begins, and fouls up the output. And it's very much like a stack buffer overflow. You override important memory areas with text like pointers and other things. This is another memory corruption vulnerability. And as you might imagine, it does not happen in Rust. You can define heap objects in Rust, and you can store them. And when you change them, it just automatically relocates them. So I can put in 20 characters long objects, and I can put in 40 characters long objects, and it just continues to be right. Name1 contains 40 and name2 contains 40. It doesn't matter how big I make them. It automatically readjusts to store them in a location where there's enough room to store them, just like it did on the stack. And you can see that in the debugger. Another issue is dangling pointers. This is another problem with C. You can allocate space for name1, and then you can free name1, and then you can print name1 after you have freed it. And if you do that, you will get, you'll end up with name1 and name2 both pointing to the same address, because what I did was I allocated space for name1, then I freed name1, then I allocated space for name2. So it will just reassign name2 to point to the same location where name1 was. So now I have two pointers that point to the same object. And this is the kind of thing that, again, makes it possible to do memory corruption by writing to a memory location that is not in fact reserved for its current use, but is left over from something that should have been deleted. And it happens pretty often because you have subroutines and other subroutines all using the same object, and one of them will free an object and the other one will not know that somebody else has already freed it. So they'll use it after it's been freed, or they'll try to free it twice, and that leads to these memory corruption vulnerabilities. And in Rust, as you might imagine, this doesn't happen. If you create an object, and then let me just get down here, there. It won't let you use the mistake. After name1 is no longer allocated, it will tell you a local variable with a similar name exists, name2, aborting due to previous error. You cannot have a value, name1. So what happened here is I defined a mutable value name1 with this box function, which allocates, I think, on the heap. Again, it finds it, and then I free name1, name2, and here's name1. Oh, I know what happened. What I did was I defined it inside this function with this bracket, so it only existed in that scope. So there was a name1, and when I left that scope, it was freed, and when I try to use it, it detects that it's gone. So anyway, that's the point, that again, this is another memory corruption vulnerability that happens in C that won't happen in Rust. All right. And there's also an example down here of a memory leak where you keep allocating space and you never free it, so it burns through things. And if you do that in Rust, it will automatically fix it. There is no free command in Rust. It automatically frees things when they come out of scope. So you don't have to manually free it. So you can't make the mistake of freeing it twice, or using it after you free it, or forgetting. In retrospect, I wonder why there is a free command in C. This would seem far more logical. So anyway, and you can show that there is no memory leak in Rust. And in C, you can have duplicate pointers pointing to the same address. And there's an issue of ownership in Rust, so I don't think I'll go through it in any detail. But again, these other errors in C have all been fixed. So that's why Rust is very popular these days. As you can see, a developer would rather use this language where the code will do what it appears to do, and there are not so many pitfalls where you write code that in fact does something very strange, not what you appear to be writing. So that's it for that one.